What's up, little veggies? Today, we're going to talk about torque and angular momentum. And this is hopefully a little familiar because we just finished our momentum unit. Um, just a disclaimer, if you feel like at the end of this video you don't have everything about momentum, don't really trip because we have another lesson on angular momentum where we do conservation of angular momentum. Today, we're really going to be focusing on changes in momentum and what causes a change in momentum. So, we're going to talk a little bit about momentum, units for momentum, changes in momentum, and then we're going to look at two different problems where the method we use to try and measure the angular momentum is a little bit different for both of them. So we will discuss the differences between both of those, and then hopefully we will, you know, be good at momentum by then. But maybe not. We'll do our best. So let's dive into it. All right. So let's talk about what is angular momentum. So if you think you understand regular momentum, it's not that different from that. So similar to how momentum is a measurement of how much something is moving, and that's intentionally left kind of vague. There's, it's how much something's moving, and when I say is moving, what I mean is how hard would it be to stop this thing, right? If it's moving more, it's harder to stop. There's a lot of inertia behind that momentum. So it's how much it's moving in that sense. The angular momentum is an object. Sorry, it's not an object. Of course, it's not an object. The angular momentum is a measure of how much something is spinning. So just like heavy things moving in straight lines, if you put yourself in front of them, you've got to push back on them to slow them down and stop them. If something is spinning, you're going to have to apply some torque to it to get it to slow down and stop spinning. Okay? So for angular momentum, we use the variable L, and the definition of angular momentum is the moment of inertia. Moment of inertia. There you go. Spelling's hard. Multiplied by the angular velocity. Okay. Just to really bring the comparison between the two of them home, regular momentum is equal to mass times velocity. So angular momentum is angular mass times angular velocity. They're the exact same thing. It's just one's for spinning and one is for going in straight lines. Okay. So what we're going to focus on today is the change in angular momentum. We want to know, how do we get things to speed up? How do we get things to slow down? And what are some ways that we could go about measuring the change in angular momentum? Because unfortunately for us, there is not an angular momentometer or momentometer, momentometer. I don't know how you would say it, but there's not a tool that you can point at a spinning thing and then it'll tell you how hard it would be to stop. So to change the angular momentum of an object, we need an unbalanced set of torques, and they have to be applied. You can't just unbalance really fast, just tap it and then let go. You have to have it applied for some amount of time. If you tap it, that amount of time is probably like 0.1 seconds. You know what I mean? It's quick, but it's not zero. So very similar to how our change in momentum, linear momentum, was force times time. Our change in angular momentum is torque times time. For our change in angular momentum, typically, and this is a little bit less true for angular stuff, but typically, our angular mass, our moment of inertia, will not really be changing. The shape of the thing won't really change, and the amount of mass the thing probably won't really change. But if it does, we're going to focus on that tomorrow or a week from now, whenever you watch the next video. And we're going to focus today on a thing that's not really malleable or bendy, changing the speed it's spinning at. We're focusing on the change in how fast it's spinning, not the shape of it changing. Okay. So if we want to measure the change in angular momentum, we can attack it in two ways. We can attack it from a torque perspective. If we can figure out the torque being applied and they tell us, or we can measure how much time that torque is applied for, that will be enough information to tell us the change in angular momentum. The other approach that we have is if we know the moment of inertia of an object and we can figure out the change in its angular velocity somehow, then using those two variables, we can still find the change in our momentum. So if you don't have all four of these at once, it's not impossible to figure out the change in your momentum. Really, all you need to know is two of them. Okay. If you want to use something here to find something here, then you need to know at least three. But we're going to try and keep them a little bit separate today. We're going to focus on, if I don't have enough information about the forces acting on the object to find the torques, or maybe I forgot to measure how much time it is, can we look at the change in velocity and the shape and mass of the object to figure out its change in momentum? Or if we don't really know the moment of inertia of something and it's too hard for us to calculate the angular velocity of the thing, if we know how hard we're trying to twist it and we know how long we do that for, that will also get us the answer. Okay. So let's go take a look at two different problems that each take one of these two approaches at trying to find our change in angular momentum. So the first one we have is a heavy disk is initially at rest. The moment of inertia of the disk is given as 1/2 mr squared, where m is the mass of this disk, and then r is going to be from the center of the axle to the edge of the disk. Okay. After 5 seconds, the disk is rotating at, this is supposed to be omega d, but it's hard to make an omega in this program. It doesn't have a lot of good font selections. So the frictional forces of the disk rotating about the axle are not negligible. So we've got some friction, but we don't really know how much friction. What is the change in angular momentum of the disk over those 5 seconds? Okay, so we have two approaches, like I said. We can either, if we're looking for our change in angular momentum, which we are, we can either take the approach of what is the unbalanced torque acting on this object and how long does it act for? Or we can take the approach of, here's our moment of inertia, and we're going to look at the change in the speed of rotation, omega, to try and find that change in angular momentum. So let's take a look at our problem and see what we know. The heavy disk was initially at rest. Okay, so we know omega naught, our initial angular velocity, is 0. Okay, the moment of inertia of the disk is given as 1/2 mr squared. Okay, so we know the moment of inertia of a disk, sort of. We don't know the actual mass of the disk, and we don't know the actual radius of the disk, but they're telling us it's this equation, so we sort of know it, and we could probably take a tape measure and measure this and get a scale and weigh this and be okay. After 5 seconds, Okay, so they told us a change in time. The disk is rotating at omega d. This is our final angular velocity. So we have the initial and the final. The frictional forces on the disk rotating about the axle are not negligible, but they don't really tell us what they are. What is the change in angular momentum of the disk over those 5 seconds? So something is speeding this disk up. They don't tell us what it is, right? Maybe there's like a rope here and they're pulling on it with some force, speeding this thing up like a Beyblade or a top, right? Maybe they have like a, how would I draw this? Like a thing on like a drill, right? They've got like I've seen they're like rubber corks, right? And you just press it up against this, so this thing spins and it speeds this thing up. This is kind of how like your starter in your car works. You've got like a little motor that spins a big disc to get the thing going. So you could have like a little thing that you press against it and it spins it up, or maybe this thing is like toothed, right? Like it's a gear, and this is a gear, and this thing is just twisting it. It's pushing on it, but they don't really tell us anything about that, so we don't know what this driving force is. And there's some friction probably slowing this thing down, but they don't tell us how much friction is there. They don't tell us where's the friction applied. What's the actual shape of this axle so that we can have a radius so that we could find the torque is force times distance from axis of rotation sine theta. So there's a bunch of information we don't know about the forces. So there's a bunch of information that prevents us from finding anything about these torques that are happening. There's a torque making it speed up somewhere. They don't even tell us about it. There's a torque from the friction slowing it down. We don't know very much about it. That kind of tells us that this centerpiece is probably not what we want to try and do. For us, we know the initial angular velocity, we know the final angular velocity, and we sort of know the moment of inertia. We can find the change in angular velocity by doing a little bit of subtraction, and we could plug in this equation for them. And that would be this full thing. So in this problem, the approach they want us to take is, instead of looking at the torques driving the system, they want us to just look at what is the change in the momentum because an object is speeding up or slowing down. So now let's just plug a few things in just to get it out of the way, and then we'll clean it up and go to the next problem. So our change in angular momentum is equal to I is 1/2 m r squared. And then change in omega is omega final minus omega initial. So our omega final is omega d. And then our omega initial was 0. So we can kind of clean this thing up a little bit. Our change in angular momentum is 1/2 m r squared omega d. And this is the best we can do with what information they've given us. Maybe they give you some numbers here. Maybe they tell you the final angular velocity. Maybe they tell you the mass of the disk, and they say, what other information would you need to figure out the change in angular momentum? You'd probably need to measure that radius as well. So you want to start by looking at these two pieces or forms of change in angular momentum and see which one you have enough information to try and fill out and make some substitutions for. Okay. I need to borrow this beautifully drawn disk here. Let's copy that. Let's bring that to the next slide. So let's look at the same disk, except this time let's turn this thing on its side. Okay, so we have a heavy disk with a mass of 50 kilograms. Okay, cool. Now they're giving us masses. and a radius of 0.2 meters. The only thing I can think of that actually has these dimensions more or less is if you've ever gone to the gym, the biggest, heaviest weights that they have for like bench press or squatting are 45 pounds. Those are 22.5 kilograms. Okay. This is about double that. So if you took two of those together, that's this thing. This is almost 100-pound big old disc. It's actually a little over 100 pounds, so it's huge. And it's about 40 centimeters across, or 20 centimeters radius. Okay. Has a moment of inertia of the same thing. This disclaimer or spoiler or informative tidbit, this is the moment of inertia equation for a rotating disc. As long as the disc is solid and it doesn't have like holes in it or anything. If it's a uniform disc, it's 1/2 mr squared. Okay. A light rope is wound around the disc, and the rope is pulled with a force of 200 newtons for 6 seconds. So we've got a rope, and this thing is pulling with a force of 200 newtons for 6 seconds. Time equals 6 seconds. Later, a student measured the angular velocity of the disc and determined that the disc had an angular, this word should be momentum, of about 200 kilograms meters per second. Okay, so our disc, if it started from rest and then we pull this rope for 6 seconds, and then our final angular momentum is 200, we had a change in angular momentum of 200. The units for angular momentum are kilograms meters per second, which is cool because those are actually the same units for regular momentum. So there's our change in momentum. What is the impulse of the friction acting on the disc? Okay, so a couple of things to break down here. We have a lot more information about the forces driving this system, which is actually the same system. I'm not going to lie. I reuse examples here, but it's the same system. We have more information. Now we know exactly the driving force. It's a 200 Newton tension from a rope, and it's being applied for 6 seconds. Because we know the torque because we know so much about the force, torque is force times radius. We know the radius, we know the mass. We can find the torque and then the change in angular momentum because of the torque from this rope. Okay, we'll put delta LR. Okay, so our rope, because we're pulling with this much force for this much time at this distance from the axis of rotation, we are going to give it some change in angular momentum. However, there is friction in this problem, and we're looking for the impulse of the friction acting on the disc. So let's just start by finding the change in angular momentum because of the rope, and then we'll kind of go from there. Let's plug in our stuff. So the torque is our force of 200 newtons times our radius, which is 0.2. This is 40 Newton meters. Okay, great. And then you might say, Mr. Brown, where did the sine theta go? This rope, we're going to say that it's being pulled straight from the edge of the circle so that these make a right angle. So the sine is 90, which is 1. So we'll get rid of it. We'll say we'll pull with the most efficient angle. Okay, so our torque is 40 Newton meters. Let's plug that in here. Delta L R. So the change in angular momentum from our rope is equal to 40 times our change in time, which is 6 seconds. This is 240 Newton meter seconds. Wait a second. I think there's an issue up here. Kilograms, meters per second. I think actual momentum is these units might be wrong. We'll come back to that. Okay. So we gain 240 momentums, newtons, meters, seconds, from this rope. Someone measured it though, and we only have 200 momentums after we've pulled on this for 6 seconds. Where did the rest of our momentum go? It went to friction. So friction took away some of our momentum. Because our disc is rotating this way, friction is going to work in the opposite direction, trying to slow it down and stop it. So it's going to take momentum out of our system. This difference in momentum between what we put in with the rope and what we measured coming out at the end, that change is the angular momentum stolen by the friction. So what's the change in angular momentum of friction? It's negative 40 Newton meter seconds. Okay. There we go. So in this approach, we're working with the torques. We're calculating change in angular momentum by doing torque times time. And then we are comparing that with what was experimentally measured. This helps us find the change in momentum of the change in angular momentum because of our friction. And that is a hard thing to measure, right? We couldn't actually just measure the friction. So this is probably an efficient way to figure out how much friction is acting in your system. So there we go. There's your introduction to angular momentum. There's two different approaches you want to take. Either look at your torques and your times, or you want to look at your change in velocities and your moments of inertia. If you can figure out a set of those, then you can find the change in angular momentum. So if you need any help with that, please let me know. Head to the website, say, Mr. Barton, you did a terrible job and I'm so confused. Let me know. Don't downvote the video though. You're gonna lower my engagement numbers or something. Actually, if you really feel that strongly about it, I suppose it's warranted. That's what the button's there for. But I encourage you to like and subscribe. Until next time, have a wonderful day, everybody.